So populations, by definition, it's all members of species living in a given area at the same time. So for example, our class makes up the population of AP Environmental. When you're going to study how populations respond to changing environments, which is the focus of this unit, that's called population dynamics. Now, populations are calculated in many, many different ways, and you're going to be responsible for learning all the ways or all the different ways scientists calculate populations or estimate sizes or estimate changes of the population. For size of a population, you basically count the number of organisms in a given area. If you look at a specific area and you look at how many are in a unit of that area, that's called population density. And population density can vary significantly from size. For example, if you look at Texas, it's a very populated state. It has a lot of members living in this state, but dense-wise, it's not overly populated because it's there. Each person has a amount of space within their area. If we look at the way organisms are dispersed, that's called dispersion, or how organisms are arranged. In this particular picture, you notice most organisms are grouped. They call that clumping. This picture, you see the plants are evenly distributed, and here it looks like random. Most populations in an environment are clumped, and there's several reasons why they live this way. Number one, resource availability. So if there's a watering hole, all elephants will clump around the watering hole. For group work, they need to work together for predator relationships or prey relationships, or resource gathering can be. They stick together for protection. The more you have, the more your chance of survival is, and obviously for mating and caring. Here's a picture of the distribution of population in the United States. This kind of shows how many people, and you could see the densely populated areas. So for example, here, there's so many people within a given area. And let's look at Florida. You see the East Coast is where it's densely populated. The whole state is populated, but you see this area where you don't have heavy population. We're going to go back to the rule of 70. It's important to know that no population can grow indefinitely because environmental resistance will come into play. So any factor that limits a population growth is considered environmental resistance. And examples of that can be resources, disease, etc. We have two major species within a population. K basically are going to reproduce at a later age in life, and they're going to have few offspring. Humans are an example of K selected species or K strategists. R reproduce young, and they reproduce reproduce young and reproduce a lot of offspring. We're going to look at biotic potential versus environmental resistance. Your capacity for growth, or basically your ability to grow as a population under ideal conditions, makes up your biotic potential. There's always going to be resistance affecting your biotic potential. And here's a graph to show that. So we're going to look at this graph, and basically the first most important factor that determines a population's growth is the carrying capacity, which is the maximum amount of species an ecosystem can support indefinitely by the environment. In easier terms, carrying capacity involves resource availability. So a population will grow and grow and grow as long as there's resources available. If you exceed your carrying capacity, populations can struggle in the end. This curve right here, which looks like a letter J, is representing exponential growth. Exponential growth is a J-shaped curve. The population booms because there's few limits, but if you exceed the carrying capacity, then the growth will eventually slow, as I mentioned before. This S-shaped curve right here basically shows a population that's increasing and eventually will stabilize or stay below the carrying capacity. S for stable. The space in the middle is what we call environmental resistance, and it determines what the population growth is. Here are some different curves to describe population changes, and unfortunately, yes, you have to know them all. This J-shaped curve, as we mentioned before, shows right here exponential growth, and then eventually there's some kind of stabilizing. So basically it's rapid growth and then steady, or exponential growth right here and then steady. Erupt, which is the green one, exceeds the carrying capacity, so it's rapidly growing, and because it exceeded the carrying capacity, there will be rapid decline of the population. In the cyclic boom bust, you're going to have increase in population followed by decrease, increase followed by decrease, always exceeding the carrying capacity. Stable, it still exceeds and goes below the carrying capacity, but since it stays right on the line, it's a slight growth and a slight decline. And irregular has no patterns. This term, intrinsic rate of increase, I've seen it come up as a vocabulary word, so make sure you know it. It's basically the rate at which a population can grow with unlimited resources. I call it an unrealistic term because we know that every resource has its limits. So let's interpret this graph. The dotted line is the carrying capacity. It's the resource availability. This J-shaped curve is what we call exponential growth. Any population that exceeds the carrying capacity is going to have limited resources. This is what we call overpopulation. When a population is overpopulated, that means resources are limited. Immediately you're going to see a decline in the population. Or you could see death, which is this line right here, or a population recovering and stabilizing, which basically stays above or below the carrying capacity.